Welcome to this journey through the vast expanse of Australia's hidden interior. As you settle in, allow your body to find a comfortable position and let your mind begin to drift with me across one of Earth's most ancient landscapes. The Australian Outback stretches before us, a seemingly endless canvas of ochre and amber, bathed in the gentle light of early morning. The sky above transforms slowly from deep indigo to soft lavender, then to pale blue as dawn breaks over this timeless land. If you're watching this video, perhaps you might share with us in the comments where you're viewing from and what time it is in your part of the world. It's always fascinating to know that while some of us are winding down for the night, others may be beginning their day with this peaceful exploration. The interior of Australia has remained largely unchanged for millions upon millions of years. The landscape we'll explore together spans approximately 5.3 million square kilometers, comprising roughly 70% of the Australian continent, yet is home to less than 10% of its population. As we embark on this geographical journey together, I invite you to join our community of gentle explorers. By subscribing to continue these peaceful journeys through Earth's most soothing landscapes. Now, let us begin our slow passage across this ancient land. Our journey begins at the very heart of the continent, where the first light of day gradually illuminates the landscape. Here, the Earth stretches out in all directions, creating an horizon so distant that it seems to curve with the very shape of our planet. The flat plains extend for hundreds of kilometers, occasionally interrupted by weathered hills that rise no more than 300 meters from the surrounding terrain. These ancient formations, known locally as breakaways, appear as islands in a sea of red earth. Their layered sedimentary structures reveal colors ranging from deep rust to pale cream, each band representing many thousands of years of geological history. The soil beneath us contains some of the oldest exposed rock formations on Earth. In some regions, these rocks date back 3.6 billion years, a span of time so vast that it becomes difficult for the human mind to comprehend. To put this in perspective, if each year were represented by a single grain of sand, you would need to count through mountains of sand to represent the age of these ancient stones. The surface of this land has been shaped not by dramatic volcanic activity or rapid tectonic movements, but by the patient, persistent forces of wind and occasional water, working gradually over unimaginable stretches of time. As the sun rises higher, shadows recede across the landscape, revealing the true colors of the Earth. The predominant red hue comes from iron oxide, essentially a fine layer of rust that coats much of the soil and stone across central Australia. This coloration varies subtly from region to region, from deep burgundy to bright terracotta, depending on the mineral composition of each particular area. In certain places, the concentration of iron oxide reaches as high as 15% of the soil composition, creating a richness of color that seems almost unnaturally vivid against the clear blue sky above. If you've ever felt drawn to these open, arid landscapes, perhaps you might share what attracts you to them in the comments below. Is it their vast openness, their ancient quiet, or perhaps their unique beauty that speaks to you? The Great Artesian Basin lies beneath much of the area we're exploring, spanning approximately 1.7 million square kilometers beneath the surface of eastern and central Australia. This massive underground water system is one of the largest of its kind in the world, with some of its waters beginning their slow journey through porous sandstone layers over 1 million years ago. The basin reaches depths of up to 3,000 meters below the surface in certain regions, containing an estimated 64,900 cubic kilometers of groundwater held within layers of permeable sandstone. Water enters this vast system primarily along the eastern edge of the basin, where rainwater seeps into exposed sandstone layers along the Great Dividing Range. From there, it begins an incredibly slow migration westward and southward through the porous rock. This water moves at an average rate of just 1 to 5 meters per year in many places, meaning that a single drop of rain falling on the eastern highlands might not complete its underground journey for tens of thousands of years. The pressure created by the weight of overlying rock forces this ancient water upward wherever the aquifer is tapped, creating natural springs, or in modern times, flowing artesian wells. These natural springs have created oases throughout the otherwise arid interior for millennia. Around these precious water sources, concentric rings of vegetation form, with moisture-loving plants clustered closest to the water, gradually transitioning to drought-resistant species as distance increases. The temperature of water emerging from deep within the basin typically ranges between 30 and 100 degrees Celsius, creating unique microclimates around these springs where specialized plant communities have evolved. The landscape continues to unfold before us as we move westward, where the iconic red center of Australia reveals itself. Here, the earth seems to glow with an internal fire, particularly in the gentle light of early morning and late afternoon. Vast plains of gibber desert pavement formed of closely packed small stones extend for hundreds of kilometers. These stones, polished by eons of wind-blown sand, create a natural mosaic across the landscape. Each individual gibber stone typically measures between 2 and 10 centimeters in diameter, usually composed of quartz, jasper, or other resistant minerals that have remained after softer materials eroded away. Their rounded surfaces reflect the sunlight differently depending on their mineral composition, creating a subtle, glittering effect across the plain when viewed from certain angles. Between these stone-covered plains lie vast stretches of red sand, forming dunes that extend like waves across the landscape. These dunes typically reach heights of 10 to 35 meters, and can extend for more than 100 kilometers in length. They are oriented generally in a northwest to southeast direction, shaped by the prevailing winds that have blown consistently from the same direction for thousands of years. The sand itself consists primarily of quartz particles, each grain measuring approximately 0.2 to 0.5 millimeters in diameter. The distinctive red coating on each grain comes from iron oxide that has accumulated over millennia, adhering to the surface of the quartz through a process of gradual oxidation. Despite appearances, these dunes are not static features. They migrate slowly across the landscape at rates typically measuring between 0.5 and 2 meters per year. This movement occurs primarily during drier periods when vegetation cover is minimal, and winds can more easily transport the sand particles. During the rare occasions when rain falls, a thin crust forms on the surface of the dunes, temporarily stabilizing them until the moisture evaporates and the slow migration resumes. The patterns created by these dune fields follow mathematical principles related to wind dynamics and particle movement. Linear dunes form parallel ridges separated by flat corridors, typically 100 to 500 meters wide. In regions where wind directions are more variable, star dunes form complex, multi-armed structures that radiate outward from a central high point. These different dune morphologies transition gradually from one type to another across hundreds of kilometers, creating a landscape that appears unchanging at first glance, yet is in a state of extremely slow, constant transformation. As the sun climbs higher in the sky, the temperature begins to increase across the landscape. The daily temperature range in the Australian interior is among the most extreme on Earth, commonly varying by 20 to 25 degrees Celsius between night and day. Summer temperatures regularly exceed 40 degrees Celsius during daylight hours, while winter nights can drop below freezing, especially in the more southerly regions. This dramatic fluctuation occurs primarily because of the minimal cloud cover and very low humidity, which allows incoming solar radiation to heat the surface intensely during the day. While at night, this heat radiates rapidly back into the atmosphere. Atmosphere itself contains remarkably few water vapor molecules, typically measuring between 10 and 20% relative humidity during daylight hours. This extreme dryness creates a clarity to the air that makes distant features appear much closer than they actually are. Mountains that appear to be perhaps 20 kilometers away might in reality be 60 or 70 kilometers distant, a perceptual distortion that has historically confused travelers unaccustomed to such conditions. Rainfall across this vast interior varies considerably, but remains minimal throughout. Annual precipitation typically ranges from 100 to 250 millimeters, with some regions receiving even less. This rain often arrives in brief, intense events that may deliver a location's entire annual rainfall in just 1 or two dramatic storms. Years may pass between significant rainfall events in some areas, creating a landscape where plant and animal life has evolved remarkable adaptations to survive extended periods of drought. When rain does fall, the transformation of the landscape can be dramatic, if temporary. Dry creek beds that have remained empty for years suddenly fill with rushing water. These ephemeral waterways, known locally as creeks despite being dry most of the time, form intricate dendritic patterns across the landscape, branching like veins or the limbs of ancient trees. The creek beds themselves are typically 5 to 30 meters wide, with sandy bottoms that may lie dormant for decades between flowing events. Perhaps some of you live near geographical features similar to what we're exploring: ephemeral waterways, ancient rock formations, or vast open plains. If you feel comfortable sharing, what natural elements near your home remind you of these Australian landscapes? Lake Eyre, or Kati Tanda, represents the lowest point in Australia at 15 meters below sea level. This vast salt lake covers approximately 9,500 square kilometers when completely filled, making it the largest lake in Australia. However, it contains water only occasionally, filling partially every 3 to 10 years, and filling completely perhaps once or twice a century. When dry, its surface consists of a crust of salt crystals, each typically measuring 1 to 5 centimeters across, creating a white expanse that contrasts starkly with the surrounding red earth. The lake lies at the terminal end of a massive internal drainage system that covers almost 1/6 of the Australian continent, approximately 1.2 million square kilometers. Rivers flow toward this basin from as far away as Queensland, over 1,000 kilometers to the northeast. Most of these watercourses are dry most of the time, carrying water only after significant rainfall events in their catchment areas. When water does arrive at Lake Eyre, most of it evaporates rather than draining to the ocean, with evaporation rates in the region exceeding 2,500 millimeters per year. The salt concentration in Lake Eyre can reach up to 40% when water levels are low, significantly higher than seawater's typical 3.5% salinity. This hypersaline environment creates conditions where few organisms can survive, yet specialized microbes have evolved to thrive in these extreme conditions. These microorganisms contain pigments that can give the shallow waters of the lake a distinctive pink or orange hue when present in large numbers. Surrounding the lake is a landscape of extraordinary flatness. The gradient of the land approaching Lake Eyre is so gentle that it typically drops only 15 to 20 centimeters per kilometer. This almost imperceptible slope creates conditions where water moves extremely slowly across the landscape during flood events, often taking weeks to travel distances that a person could walk in a day. As we continue our journey and the day progresses, we encounter one of Australia's most iconic geological features rising from the plains. Uluru stands 348 meters above the surrounding landscape, with a circumference of 9.4 kilometers. This monolithic formation is not, as sometimes described, the world's largest monolith, but rather an exposed portion of a much larger rock formation that extends several kilometers below the surface. The visible portion represents only the uppermost part of a vast sandstone rock that has been tilted almost 90 degrees from its original horizontal position through tectonic forces operating over hundreds of millions of years. The sandstone that forms Uluru was deposited approximately 550 million years ago, when this entire region lay at the bottom of a shallow sea. The individual sand grains that comprise the rock are remarkably uniform in size, averaging about 0.25 millimeters in diameter, indicating deposition in a low-energy marine environment. Over subsequent eons, these sand particles were cemented together under immense pressure as layers of sediment accumulated above them, creating the arkose, a type of sandstone particularly rich in feldspar minerals. The distinctive red color of Uluru comes from the oxidation of iron-bearing minerals within the rock, a process that has been ongoing for millions of years. Fresh samples from deep within the formation appear gray rather than red, revealing that the iconic coloration is essentially a form of rust that has developed on the exposed surfaces. This weathering process continues extremely slowly, with individual sand grains occasionally loosening and falling away during heavy rain events, gradually altering the shape of the formation over geological time. Surface of Uluru features numerous erosional patterns, including fluted channels that run vertically down its sides. These channels, typically measuring 1 to 3 meters wide and up to 10 meters deep, have formed over millions of years as rainwater follows the same paths down the steep sides of the rock, gradually wearing away the sandstone. The spacing between these channels follows a remarkably consistent pattern determined by water flow dynamics and the uniform composition of the rock itself. Approximately 30 kilometers to the west of Uluru lie the 36 domed formations of Juda, also known as the Algas. These distinctive domes rise up to 546 meters above the surrounding plain and cover an area of approximately 21.68 square kilometers. Unlike Uluru, which consists of a relatively uniform arkose sandstone, Juda is composed of conglomerate, a sedimentary rock containing rounded pebbles and boulders of multiple rock types cemented together by a matrix of sand and mud. The individual clasts embedded within this conglomerate range in size from small pebbles measuring just a few millimeters across to boulders more than 30 centimeters in diameter, indicating deposition in a high-energy environment such as an ancient river delta. The spaces between these dome formations create sheltered valleys where water can occasionally collect, supporting pockets of vegetation that differ markedly from the surrounding arid landscape. These valleys typically measure between 100 and 500 meters wide, with steep walls rising on either side that provide shade during parts of the day, creating microclimates where temperatures can be several degrees cooler than the exposed plains. The rock faces of both Uluru and Juda absorb heat differently throughout the day, creating subtle air currents as warmer air rises along sun-facing surfaces. These air movements are typically gentle, with velocities rarely exceeding 5 kilometers per hour, except during storm events. Yet, over millennia, these consistent patterns of air movement have contributed to the erosional processes that continue to shape these formations with imperceptible slowness. Many people find peaceful sleep comes more easily when thinking about natural landscapes. If you feel comfortable sharing, what elements of nature do you find most relaxing to visualize as you drift toward sleep? As afternoon transitions to evening across the Australian interior, the quality of light changes dramatically. During the golden hour, when the sun sits between 10 and 2 degrees above the horizon, the low angle of light intensifies the red hues of the landscape. Shadows extend across the plains, stretching to lengths 10 to 15 times longer than the objects casting them. This elongation creates patterns of dark and light that accentuate the subtle contours of the land, revealing topographical features that remain nearly invisible during the harsh light of midday. The temperature begins its daily decline, often dropping at a rate of approximately 0.5 degrees Celsius every 15 minutes as the sun approaches the horizon. This cooling triggers a series of subtle changes across the landscape. Certain flowering plants that have remained closed during the heat of the day begin to open, releasing scents that can carry surprising distances in the still evening air. The surface of exposed rock formations, having absorbed solar radiation throughout the day, now begins to release this stored heat, creating a gentle upward movement of air that can sometimes be detected as a slight warming sensation when standing near large outcrops. The vegetation of Australia's interior demonstrates remarkable adaptations to the harsh conditions. Across vast stretches of the region, plants are spaced at intervals, typically ranging from 2 to 15 meters apart, creating a landscape that appears sparse, yet follows specific ecological patterns related to root competition and moisture availability. Many plant species feature specialized root systems that extend horizontally for distances far greater than the height of the plant above ground. A seemingly modest shrub, standing perhaps 1 meter tall, may possess roots extending 15 to 20 meters in all directions, allowing it to collect moisture from a substantial area after the rare rainfall events. Mulga woodlands cover significant portions of the interior, typically in regions receiving between 200 and 250 millimeters of annual rainfall. These woodlands consist primarily of acacia anura trees, commonly reaching heights of 3 to 5 meters, though remaining relatively widely spaced with typically 10 to 30 meters between individual trees. The foliage of these trees has evolved to minimize water loss, with leaves reduced to flattened phyllodes that hang vertically to reduce direct exposure to the sun. These phyllodes typically measure 5 to 10 centimeters in length and just 1 to 1.5 millimeters in width, with a dull gray-green coloration that reflects rather than absorbs solar radiation. The arrangement of branches and phyllodes in mulga trees creates a distinctive canopy architecture that channels rainwater down the branches and trunk during precipitation events. This channeling effect can direct up to 25% of total rainfall to the base of the tree, significantly increasing moisture availability for its root system. The soil directly beneath a mature mulga tree often contains up to 30% more moisture than surrounding areas, creating microhabitats where certain understory plants and soil organisms can survive. In regions receiving less rainfall, the vegetation transitions to hummock grasslands dominated by spinifex grasses. These distinctive plants grow in circular clumps, typically measuring between 0.5 and 2 meters in diameter, with sharp, needle-like leaves radiating outward from the central mass. The spacing between individual hummocks generally ranges from 2 to 10 meters, creating a polka dot pattern across the landscape when viewed from above. The circular growth pattern of these grasses is an adaptation that maximizes rainwater collection, as precipitation landing anywhere on the hummock tends to drain toward the center where it can be absorbed by the plant's root system. The internal structure of spinifex grasses reveals further adaptations to aridity. The leaves contain specialized cells with thickened walls that help reduce water loss, while the abundant silica content makes them resistant to herbivory. This silica content typically comprises between 2 and 5% of the dry weight of the leaves, explaining their extraordinarily abrasive texture. The center of older spinifex hummocks often dies back, creating ring-shaped structures known as fairy circles that can persist for decades, slowly expanding outward at rates of approximately 2 to 3 centimeters per year. As evening deepens across the landscape, the temperature continues its steady decline. On clear nights, which constitute approximately 75 to 80% of nights in this region annually, the temperature may drop by 15 to 20 degrees Celsius from the daytime maximum. This dramatic cooling occurs primarily because of the minimal water vapor in the atmosphere, which allows thermal radiation to escape rapidly into space. The first few hundred meters of air above the ground cool most quickly, creating a temperature inversion where cooler, denser air settles close to the surface, while slightly warmer air remains above. This temperature inversion affects sound propagation across the landscape in interesting ways. During these calm, clear evenings, sounds can travel surprising distances with minimal distortion. A sound that might be audible at a distance of perhaps 1 kilometer during the heat of the day might carry 3 or even 4 kilometers under evening conditions. The still air allows sound waves to travel with reduced absorption and scattering, creating an acoustic environment of remarkable clarity despite the vast open spaces. As darkness falls completely, the sky reveals one of the most spectacular features of the Australian interior, its night sky. With minimal light pollution across most of this vast region, the darkness reaches levels rarely experienced in more populated areas. Sky brightness measurements typically register between 21.5 and 22 magnitudes per square arcsecond, approaching the theoretical limit for darkness on Earth. Under these conditions, the human eye can typically perceive stars down to magnitude 6.5 or even 7, meaning approximately 7,000 to 10,000 individual stars may be visible simultaneously under optimal conditions. The Milky Way appears not as a faint smudge, but as a brilliant, structured band stretching across the sky, with distinct regions of greater and lesser density clearly visible to the naked eye. The galactic center, located in the direction of the constellation Sagittarius, appears particularly bright from this southern hemisphere vantage point during certain months of the year. The individual stars that comprise our galaxy number approximately 100 to 400 billion, though of course only a tiny fraction are visible to the unaided human eye. The light from these stars has traveled between hundreds and thousands of years to reach us, meaning we observe them not as they are now, but as they were in the distant past. What elements of the content we've explored so far do you find most conducive to peaceful rest? Perhaps it's the descriptions of vast open spaces, the slow geological processes, or the gentle rhythms of the desert environment. Your reflections help us create more content that supports restful sleep. The clarity of the atmosphere allows for exceptional observation of celestial objects beyond our galaxy as well. Under optimal conditions, the Andromeda Galaxy, located approximately 2.537 million light-years from Earth, appears as an oval smudge measuring roughly 3 by 1 degrees of arc in the night sky. This makes it technically visible to the naked eye despite its enormous distance, a remarkable reminder of the scale of our universe. The light we observe from Andromeda began its journey toward Earth around the same time that early hominid species were first appearing on our planet. Closer to the horizon, particularly in the southern sky, the large and small Magellanic Clouds appear as detached portions of the Milky Way. These dwarf galaxies orbit our own galaxy at distances of approximately 163,000 and 206,000 light-years, respectively. The Large Magellanic Cloud spans approximately 9 degrees of arc in the night sky, roughly equivalent to 18 full moon diameters placed side by side. It contains approximately 30 billion stars, making it roughly 1/30th the size of our own galaxy in stellar population. The movement of celestial objects across the night sky occurs at a rate determined by Earth's rotation. Stars appear to move approximately 15 degrees per hour, or 0.25 degrees per minute, from east to west across the sky. This movement is imperceptible when observing casually, becoming apparent only through deliberate attention to the position of stars relative to stationary terrestrial features over extended periods. This slow, steady progression has remained essentially unchanged for all of human history, creating a celestial clockwork of profound constancy above the equally ancient landscape below. Beneath this spectacular sky, the nighttime landscape of the Australian interior takes on different characteristics. The reduced temperatures affect the thermal properties of different materials in interesting ways. Rock formations that absorbed heat throughout the day now radiate this energy at rates determined by their specific mineral composition. Sandstone typically cools more rapidly than denser rocks like granite or basalt, creating subtle temperature differentials across the landscape. These differences can sometimes be detected as variations in air temperature when moving from one area to another, even in complete darkness. The nocturnal ecology of the region reveals adaptations to both the aridity and the dramatic daily temperature fluctuations. Many animal species remain inactive during daylight hours, emerging only after sunset when conditions become more favorable. These creatures have evolved specialized physiological mechanisms to conserve water, many requiring no drinking water at all, extracting sufficient moisture from their food sources to survive. Certain desert mammals produce highly concentrated urine containing up to 25% dissolved solids, compared to the 5% typical of non-desert species, allowing them to retain dramatically more water within their bodies. Many plants throughout the interior have similarly adapted to maximize water retention. Succulent species store water in specialized tissues, with water content sometimes comprising up to 95% of their total mass. The epidermis of these plants often features a thick, waxy cuticle that reduces evaporation, sometimes supplemented by a sparse covering of fine hairs that create a boundary layer of still air adjacent to the plant's surface, further reducing moisture loss. These adaptations allow certain plant species to survive months or even years between significant rainfall events. The soil across much of the interior presents another fascinating aspect of this environment. Its composition varies considerably from region to region, but typically consists of 60 to 80% sand particles, 10 to 30% silt, and 5 to 15% clay, with minimal organic content, usually less than 1% by volume. This composition creates soils with high porosity but poor water retention characteristics. When rain does fall, it tends to penetrate quickly to depths of 30 to 50 centimeters before the soil's limited capillary action prevents further downward movement without additional precipitation. The mineral content of these soils reflects the geological history of the continent. Many areas feature unusually high concentrations of certain elements due to the stable geological conditions that have prevailed for millions of years. The weathering of ancient rock formations has gradually released minerals that have accumulated in the soil rather than being washed away to the ocean, as occurs in regions with higher rainfall. This has created areas where elements like iron can comprise up to 15% of the soil composition, contributing to the distinctive red coloration across vast stretches of the interior. Soil temperature fluctuations follow patterns similar to air temperature, but with dampened extremes and time delays. At a depth of 10 centimeters, the daily temperature range typically spans 15 to 20 degrees Celsius, compared to the 20 to 25 degree range for air temperatures. This fluctuation decreases with depth, so that at 1 meter below the surface, the daily temperature variation reduces to just 1 or 2 degrees. At depths beyond 10 meters, the temperature remains nearly constant year-round, typically matching the annual average surface temperature for that specific location. This stability creates a stratified thermal environment beneath the surface, with each layer exhibiting different properties. During summer months, a person digging into the soil would experience decreasing temperatures with depth, while in winter, the opposite occurs. The deeper soil feels progressively warmer compared to the surface layers. This phenomenon has historically been utilized by people living in these regions, with underground structures providing natural cooling during hot periods and relative warmth during colder times. The hydrology of the Australian interior presents a study in extremes and adaptations. The vast majority of the landscape experiences what hydrologists classify as endorheic drainage, water that falls as precipitation does not ultimately reach the ocean, but remains within the internal drainage basin until it evaporates. Approximately 1.3 million square kilometers of Central Australia features this type of drainage pattern, creating a hydrological system that operates quite differently from those familiar to people living in coastal regions. When significant rainfall does occur, typically during infrequent cyclonic events that penetrate far inland, or from the occasional monsoon systems that extend unusually far south, the response of the landscape can be dramatic. Dry riverbeds that have contained no water for years suddenly fill, with water moving across the landscape in complex patterns determined by extremely subtle variations in topography. A difference in elevation of just 10 to 20 centimeters can determine the direction of water flow across distances of many kilometers. These sporadic flood events typically last for relatively brief periods, though their effects can persist much longer. Water may flow in major channels for periods ranging from several days to several weeks before the combination of evaporation, infiltration into the soil, and the cessation of rainfall input causes the surface water to disappear. During particularly substantial events, water may reach Lake Eyre, where it forms a shallow inland sea that rarely exceeds 1.5 meters in depth, even at its maximum extent. The hydrogeology beneath the surface operates on dramatically different timescales. The aforementioned Great Artesian Basin contains water that has been dated using isotopic techniques to ages ranging from several thousand to over 1 million years. This ancient water moves through the porous sandstone aquifers at rates typically measuring between 1 and 5 meters per year, creating a subterranean hydrological system that operates essentially independently of surface conditions on human timescales. As night progresses toward early morning across the Australian interior, temperatures typically reach their minimum approximately 30 to 45 minutes before sunrise. During winter months in the southern portions of the region, these temperatures can fall below freezing, with readings of to -5 degrees Celsius not uncommon in June and July. When these conditions occur, the minimal moisture present in the atmosphere can condense directly from vapor to solid form, creating a light coating of frost across the landscape. This frost typically forms most heavily on objects that cool rapidly through radiative heat loss, such as exposed rock surfaces and the leaves of plants. The distribution of frost across the landscape reveals subtle variations in local conditions that might otherwise go unnoticed. Areas with slightly higher humidity, often associated with minor depressions or the presence of certain types of vegetation, develop heavier frost. Similarly, locations with marginally higher elevation often experience less frost due to improved air circulation that prevents the most extreme cooling. The human geography of Australia's interior presents a study in sparseness and adaptation. The population density across most of this vast region averages less than 0.1 persons per square kilometer, making it one of the least densely populated substantial land areas on Earth. Settlements follow particular patterns, typically located either near reliable water sources, along transportation corridors, or at locations where specific resources can be extracted. These settlements range in size from isolated homesteads to small towns, rarely exceeding a few thousand inhabitants. The spacing between these population centers creates a landscape where the next human habitation may be 50, 100, or even 200 kilometers distant. Distances that have profound implications for how life is organized in these regions. Services that urban dwellers might consider basic necessities, such as medical care or education, often require journeys of several hours or more, creating patterns of life that revolve around careful planning and self-sufficiency. The architecture of human habitations in the interior reflects adaptations to the challenging environmental conditions. Traditional structures often feature thick walls with high thermal mass, typically constructed from locally available materials such as stone, rammed earth, or in more recent times, concrete. These materials absorb heat slowly during the day and release it gradually at night, helping to moderate interior temperatures despite the extreme external fluctuations. The thickness of these walls typically ranges from 30 to 60 centimeters, providing substantial insulation value through sheer mass, rather than through the modern approach of creating dead air spaces within wall cavities. Roof designs frequently incorporate significant overhangs, extending 60 to 100 centimeters beyond the walls to provide shade during summer months when the sun angle is high, while still allowing lower angle winter sunlight to reach windows and warm the interior. Ventilation systems, whether traditional or modern, are designed to take advantage of temperature differentials to create air movement without mechanical assistance. Many structures incorporate features like clerestory windows, placed high on walls to allow hot air to escape, or carefully oriented openings that capture prevailing breezes during certain times of day. The economic activities across the interior primarily revolve around extensive rather than intensive land use. Pastoral operations typically require enormous areas to be viable in this arid environment, with cattle stations often encompassing 1,000 to 10,000 square kilometers or more. The stocking rates on these properties reflect the limited carrying capacity of the land, with figures typically ranging from 1 animal per 10 hectares in more productive areas to 1 animal per 100 hectares or more in the most arid regions. Mining represents another significant economic activity throughout the interior. The stable geological conditions that have prevailed for millions of years have allowed for the concentration of various minerals into economically significant deposits. These operations typically create distinctive landscapes where the natural environment is substantially modified, with open pit mines sometimes reaching depths of 500 meters or more below the surrounding surface. These artificial depressions create their own microclimates, with temperatures at the bottom of deep pits often differing from those at the surface by 2 to 3 degrees Celsius due to limited air circulation and different patterns of solar exposure. Which aspects of our exploration so far do you find most conducive to peaceful sleep? Is it the descriptions of vast open spaces, the slow geological processes happening over millions of years, or perhaps the regular patterns of day and night in this ancient landscape? Understanding what elements help you drift toward sleep allows us to create even more effective content for those seeking peaceful rest. transportation, networks across the interior display patterns distinctly different from those in more densely populated regions. Roads typically follow remarkably straight paths over vast distances, with curves necessary only to navigate around major topographical features. These roadways, often unpaved outside major routes, create linear features visible from satellite imagery as straight lines extending for tens or even hundreds of kilometers across the landscape. The spacing between these transportation corridors can be substantial, with distances of 50 to 200 kilometers between parallel routes not uncommon in the most remote regions. The night gradually gives way to early morning, and the first hints of dawn appear along the eastern horizon. The process begins with a subtle lightening of the sky, approximately 30 to 45 minutes before the sun itself appears. This pre-dawn illumination occurs gradually, with the brightness of the sky increasing at an almost imperceptible rate initially, then accelerating as the sun approaches the horizon. During this period, the landscape remains largely in shadow, appearing in silhouette against the increasingly bright eastern sky. As the sun finally emerges above the horizon, its light reaches the landscape at an extremely low angle, typically between 0 and 5 degrees during the first few minutes of daybreak. This grazing illumination accentuates even the most subtle topographical features, casting shadows from objects that might appear insignificant during other times of day. A small stone projecting just 5 centimeters above the surrounding surface can cast a shadow extending several meters across the ground, creating a temporary prominence that will disappear as the sun climbs higher. The temperature, having reached its minimum shortly before dawn, now begins its daily ascent. The rate of this warming typically begins slowly, with increases of perhaps 0.2 to 0.3 degrees Celsius per 15 minutes during the first hour after sunrise. This rate accelerates through the morning hours, often reaching 0.5 to 0.7 degrees per 15 minutes by mid-morning. The landscape absorbs this solar energy differentially, with dark-colored surfaces warming more rapidly than lighter ones, and dense materials like stone heating more slowly than loose sand or soil. This differential heating creates subtle air movements across the landscape as warmer air above heated surfaces rises and is replaced by cooler air flowing in from surrounding areas. These microscale circulation patterns rarely involve wind speeds exceeding 5 to 8 kilometers per hour, but contribute to the overall atmospheric dynamics of the region. They also influence the distribution of moisture, as evaporation rates increase substantially over warmer surfaces, creating almost imperceptible variations in humidity across the landscape. The cycle of day and night, of warming and cooling, of light and shadow, continues as it has for millions of years across this ancient landscape. The geological processes that that shaped the Australian interior operate on timescales that make human history seem momentary by comparison. Erosion gradually wears down exposed rock formations at rates typically measuring between 1 and 10 millimeters per thousand years, depending on local conditions. Even this seemingly slow process has been sufficient to reduce what were once towering mountain ranges to the modest elevations we observe today. Given the vast spans of time available, the biological communities that inhabit this landscape have evolved in concert with these geological processes, developing adaptations that allow survival in conditions that would prove fatal to organisms from more temperate environments. Plants have modified their physical structures, their biochemical processes, and their reproductive strategies to thrive in an environment where water is scarce and temperatures fluctuate dramatically. Animals have similarly evolved specialized behaviors, physiological mechanisms, and life cycle patterns that allow them to persist despite the challenging conditions. The interconnectedness of these biological systems reveals itself through careful observation. Certain plant species provide habitat for specific insects, which in turn serve as food sources for particular reptiles or birds, creating ecological networks of remarkable complexity despite the apparently sparse distribution of life across the landscape. These relationships have developed over millions of years of coevolution, creating balanced systems that persist through seasonal changes and even through extended drought periods that might last for several years. The human presence in this landscape is relatively recent from a geological perspective, with indigenous habitation dating back approximately 65,000 years, according to current archaeological evidence. This represents less than 0.02% of the time that has elapsed since the formation of the oldest rocks in the region. Yet even this comparatively brief period has been sufficient for human cultures to develop sophisticated knowledge systems about the environment, including detailed understanding of water sources, food availability, and navigation across vast distances without the aid of modern technology. As the morning progresses and the sun continues its ascent, the colors of the landscape shift subtly. The rich reds of distant formations become slightly muted as the intensifying light reduces the contrast between shadowed and illuminated areas. The sky typically remains clear, with a distinctive deep blue coloration that results from the minimal water vapor and particulate matter in the atmosphere. On the horizon, however, the blue transitions to a paler hue, a visual effect created by the greater atmospheric thickness when looking toward the horizon rather than directly overhead. The surface temperature of exposed soil and rock begins to increase more rapidly, often reaching 45 to 60 degrees Celsius by mid-afternoon during summer months. This creates a layer of heated air immediately above the ground that can cause the distinctive heat shimmer visible when looking across long distances. This optical phenomenon results from the refraction of light through air layers of different densities, creating the illusion of water on distant surfaces, or making objects appear to waver slightly when observed from afar. The daily cycle continues its gradual progression as noon approaches. Shadows shorten progressively as the sun climbs higher in the sky, reaching their minimum length when the sun attains its maximum elevation for the day. At the latitude of central Australia, approximately 25 degrees south, the noon sun never quite reaches directly overhead, instead remaining slightly to the north, even on the summer solstice. This creates a slight but persistent southward bias to shadows throughout the year, a subtle orientation indicator that becomes more pronounced during winter months, when the sun's maximum elevation may reach only 40 to 45 degrees above the northern horizon. The apparent stillness of the landscape masks the continuous but extremely slow processes of change that reshape it over geological time. Wind gradually moves sand particles across the surface, typically at rates of just a few centimeters per day under normal conditions. Occasional stronger wind events may move substantial amounts of material in short periods, but these episodic changes average out to relatively consistent long-term rates of landscape evolution. Over thousands of years, these almost imperceptible daily movements accumulate to create significant alterations to the distribution of materials across the landscape. Chemical weathering processes simultaneously work to break down exposed rock surfaces. The daily heating and cooling cycle causes minute expansion and contraction of different minerals within the rock, gradually weakening the bonds between them. This thermal stress typically causes cracks to develop at rates measuring just micrometers per year. But over thousands of years, these accumulate to create substantial fissures that eventually lead to the fragmentation of larger rock masses into smaller components. The minimal but occasionally intense rainfall contributes to these weathering processes. When water does penetrate cracks in rocks, it can dissolve certain minerals, creating additional space within the crack. If this water later evaporates, it may deposit different minerals that exert expansive pressure as they crystallize, further widening the opening. This process, occurring perhaps only a few times annually during rain events, nonetheless contributes significantly to the overall weathering regime over extended periods. The rate of chemical weathering in this environment typically ranges from 0.5 to 2 millimeters per 1,000 years, depending on rock type and local conditions. Beneath the surface, in the soil layers that appear so unchanging, equally slow processes continue without pause. The limited organic material present gradually decomposes through the action of specialized microorganisms adapted to function in the high temperature, low moisture environment. This decomposition typically occurs at rates 5 to 10 times slower than those observed in more temperate environments due to the moisture limitations, meaning that a leaf falling to the ground might require 5 to 10 years to completely break down into its constituent compounds. The soils themselves gradually evolve through complex interactions between physical and biological processes. Wind-transported materials arrive from distant sources, adding new mineral components to the existing mixture. The extremely slow vertical movement of fine particles through the soil column, typically measuring just millimeters per century, gradually creates distinct layers with different physical and chemical properties at various depths. These soil horizons develop at rates proportional to the environmental conditions, with soil formation in arid regions typically occurring 10 to 20 times slower than in areas with abundant rainfall. As afternoon progresses across the landscape, the temperature reaches its daily maximum, typically occurring between 2 and 3 hours after the sun's peak elevation. This lag results from the continuing accumulation of heat in the surface materials, even after the intensity of incoming solar radiation begins to decrease from its midday peak. During summer months, these maximum temperatures commonly reach 40 to 45 degrees Celsius in the shade, with exposed surfaces becoming considerably hotter. Measurements of surface temperatures on dark rocks during summer afternoons have recorded values exceeding 70 degrees Celsius, hot enough to cause serious burns if touched with bare skin. The atmosphere above the heated landscape develops vertical circulation patterns as warm air rises from the surface and is replaced by cooler air from above. These convection cells typically extend to heights of 3 to 5 kilometers above the surface during maximum heating periods, occasionally forming cumulus clouds if sufficient moisture is present in the upper levels of the cells. More commonly in this arid environment, the convection remains dry, with no visible cloud formation due to insufficient atmospheric moisture content. These rising air columns can sometimes develop sufficient velocity to entrain dust particles from the surface, creating dust devils, rotating columns of air visible due to the suspended particles they contain. These transient features typically measure 5 to 50 meters in height and 1 to 10 meters in diameter, moving across the landscape at speeds of 5 to 15 kilometers per hour. They generally persist for periods ranging from 30 seconds to several minutes before dissipating as the organizing thermal gradient weakens or surface irregularities disrupt the rotational pattern. The apparent emptiness of the landscape conceals remarkable biodiversity adapted specifically to these challenging conditions. The flora of the Australian interior includes approximately 5,000 to 6,000 species of vascular plants, many of which occur nowhere else on Earth. These plants display a remarkable range of adaptations to aridity, including modified leaf structures to reduce water loss, specialized root systems to maximize water uptake, and biochemical pathways that function efficiently at the high temperatures commonly experienced during summer months. Many plant species have evolved life cycles specifically adapted to the unpredictable rainfall patterns of the region, rather than following annual rhythms determined primarily by temperature or day length. As in more temperate regions, these plants remain dormant, sometimes for years, until sufficient rainfall triggers a rapid growth and reproductive phase. Seeds can remain viable in the soil for extraordinary periods, with some species demonstrating germination capability after 10 or even 20 years of dormancy under appropriate laboratory conditions. The seed banks contained within the soil represent a fascinating aspect of this environment's ecology. A typical square meter of soil may contain between 1,000 and 5,000 viable seeds from 20 to 50 different plant species, creating a reservoir of potential life that remains invisible until appropriate conditions trigger germination. This adaptation allows plant communities to persist through extended drought periods that might otherwise eliminate them entirely from the landscape. The density and composition of these seed banks vary across the landscape in patterns related to soil type, topography, and historical vegetation patterns. Animal life, though less immediately visible than the plant communities, demonstrates equally remarkable adaptations to the arid conditions. Approximately 200 to 250 species of birds inhabit the region, many following nomadic movement patterns determined by resource availability rather than fixed migratory routes. These birds typically disperse widely during drier periods, then congregate in areas where recent rainfall has triggered increases in food availability. Their movements can span hundreds or even thousands of kilometers as they track resources across the vast landscape. Reptile diversity is particularly high, with 100 to 150 species typically found across the arid interior. These animals have evolved physiological adaptations that allow them to conserve water exceptionally efficiently. Many species obtain sufficient moisture entirely from their food, never drinking free water even when it becomes available. Their metabolic rates adjust seasonally, decreasing substantially during cooler months when food resources may be more limited, allowing them to survive extended periods with minimal energy intake. As the afternoon wanes and the sun begins its descent toward the western horizon, the landscape enters another transition phase. The angle of illumination gradually decreases, creating lengthening shadows that once again accentuate the topographical features that appeared flattened during the harsh midday light. The color palette shifts subtly, with the reds and oranges of the landscape intensifying as the light wavelengths must travel through more atmosphere to reach the surface, resulting in greater scattering of the shorter blue wavelengths. The temperature begins its evening decline approximately 1 to 2 hours before sunset, initially at a relatively modest rate of perhaps 0.2 to 0.3 degrees Celsius per 15 minutes. This cooling accelerates as the sun approaches the horizon, often reaching rates of 0.5 to 0.7 degrees per 15 minutes during the hour following sunset. The differential cooling of various surface materials creates subtle thermal boundaries across the landscape, with areas of exposed bedrock releasing their stored heat more slowly than surrounding soil or sand surfaces. These thermal gradients influence local air movements during this transition period. As some areas cool more rapidly than others, the density differences in the air create gentle flows, typically measuring just 3 to 8 kilometers per hour. These air movements follow topographical features, with cooler, denser air flowing downslope into depressions where it can accumulate to depths of several meters. This cold air drainage creates microclimate variations that can result in temperature differences of 2 to 3 degrees Celsius between adjacent areas separated by elevation differences of just 10 to 20 meters. The sky transforms through a spectrum of colors as the sun approaches and then drops below the horizon. The process typically begins with the development of golden hues approximately 30 to 45 minutes before sunset, transitioning through deepening orange and eventually to red tones as the solar disk makes contact with the western horizon. After the sun disappears from view, these colors continue to evolve for 20 to 30 minutes in the afterglow, often producing the most vibrant hues of the entire sequence during the period 5 to 15 minutes after the sun has set. This optical display results from the scattering and absorption of different wavelengths of light as they pass through increasing thicknesses of atmosphere near the horizon. The specific colors and their intensity vary considerably depending on atmospheric conditions, particularly the amount and type of aerosols present in the air. On days following rainfall, when the air contains minimal dust, the sunset colors tend toward clearer oranges and reds. During periods when bushfires have introduced smoke particles into the atmosphere, these colors often shift toward deeper reds and even purples due to the specific light-scattering properties of the smoke particles. As the day completes its cycle and darkness once again envelops the landscape, the processes we've explored continue their patient work. The geological forces that have shaped this ancient landscape for millions of years persist, operating at timescales far beyond human perception, yet maintaining the continuous transformation of the environment. The biological communities complete another cycle of their existence, having endured the challenges of another day in this demanding, yet remarkably beautiful landscape. If our journey through Australia's hidden interior has helped create a peaceful state conducive to rest, Perhaps you might consider subscribing to join us for future geographical explorations. Our next journey may take us to other landscapes with their own unique rhythms and patterns. Perhaps the misty highlands of Scotland, the gentle plains of Hungary, or the meandering rivers of the Amazon basin. Wherever we travel next, we'll continue to explore the soothing aspects of Earth's diverse environments, creating spaces for reflection, relaxation, and eventually, peaceful sleep. The cycles we've observed of day and night, of geological processes measured in millions of years, of life adapting to challenging conditions, remind us of the continuous, patient rhythms that have persisted long before human existence and will continue long after. There is something deeply comforting in this perspective, in recognizing our place within these greater patterns. As you drift toward sleep, perhaps carry with you an image of this ancient landscape under its canopy of stars, existing in its timeless way, undisturbed by the hurried pace of human concerns, continuing its gradual transformations beneath the vast Australian sky.